transformers like Optimus Prime and Bumblebee don't need drivers on their steering wheel. They act on their own and save the Earth from Decepticons. But our electrical transformers need gate drivers to save and insulate the high-side power electronic switches in the circuit. This time we'll see the construction and working of double-ended transformer-coupled gate drives, and we'll also consider a small example where we'll select a driver IC and potential double-ended transformer-coupled gate driving circuitry considering an example. So let's start. Whenever we use a half-bridge or full-bridge converters, the circuit needs 2 or more high-speed switching transistors. In this case, we use push-pull double-ended PWM controllers where a driving circuit controls both high-side and low-side switches at a time. When these type of converters are working at high voltage or power, we have to electrically isolate the driving logic circuit and high power circuit. To do so, we use double or multiple ended transformer coupled gate drives depending upon the number of switching elements. Initially, we'll see what a double-ended transformer coupled gate drive circuit looks like. Let's consider a dual-channel MOSFET driving IC. This IC controls both high-side and low-side MOSFET. We'll take a double-ended transformer with 1 primary and 2 secondaries, with the windings like shown in the circuit. The turns ratio of this transformer should be 1:1:1. The phase of the first secondary winding is equal to the primary winding, and phase of the second secondary winding is opposite to the primary winding. We connect high-side and low-side MOSFET switches to both of these secondary windings after a gate resistor and gate-to-source resistor. The MOSFET driver has 2 output pins, out A and out B, which usually takes care of high-side and low-side MOSFET in case of general application. But here, we connect the primary winding to these pins. Now, we'll see how it works. In the first clock cycle, we provide signal from out A, which sends a positive voltage signal across the primary winding of the gate transformer. This time, voltage induces at the first secondary winding in the same polarity as that of primary winding, so it generates a positive VGS to turn on the high side MOSFET. And the induced voltage at the second secondary side would be negative, which will turn off the low side MOSFET. In the next cycle, out B is energized for the same amount of time, and the current will flow like this, providing an opposite polarity voltage across the primary winding of the transformer. This time, the phase of the second secondary winding is opposite, so the induced voltage would be positive, and the low side switch will turn on, and the high side switch will be off due to the negative voltage at the gate. This cycle keeps on repeating. In this way, both high side and low side switches turn on and turn off one after another. The duty cycle of this circuit is generally less or equal to 50%, which is sufficient for half-bridge or full-bridge converters. It is like a sliding window. You can either open the right side or the left side at a time. And this is how double-ended transformer-based gate driver circuit works. Now, let's take the example of this circuit. As we saw, we can use low-side driver IC to deliver the high currents needed for charging the gate capacitance of the power switches. For this application, the gate driver IC must have a current sink or source output feature to differentially drive the primary side of the pulse transformer. Since the magnetizing current of the transformer is added to the gate currents, the output current of the driver can change polarity. Therefore, the output stage of the driver IC must be capable of handling bidirectional current when coupled with pulse gate transformer. Let's construct a real-world circuit. Well, we saw this type of driving technique is used in high voltage or current requirements. Let's consider there is an application where the input voltage is 400 volts DC, and we have to use high side and low side MOSFET switching. For now, we'll ignore the type of power electronic converter, whether it is half bridge converter or full bridge converter, we don't know. The driving voltage of the MOSFET would be 12 volts. The isolation between driving circuit and actual power electronic circuit is must. Switching frequency of the power electronic converter is 200 kHz. So in this case, we need to select a dual channel driver IC which can drive our MOSFET. We'll use one of the driver ICs from the 2EDN dual channel driver IC family from Infineon. It has two outputs, out A and out B, which are supposed to be connected to the primary side of the transformer. It has very fast slew rates of 6 nanoseconds and only 19 seconds propagation delay for fast MOSFET switching. Each driving channel is capable of handling 4 ampere current. It has an undervoltage lockout to ensure MOSFET protection in case of abnormal conditions. It has 5 ampere reverse current robustness, which eliminates the need for protection circuitry. We can provide voltage up to 20 volts to the gate driver. And this is the internal block diagram of the driver IC, which suits best for our application. We'll connect the out A and out B to the primary winding of our transformer along with coupling resistor and coupling capacitor. If you want to know why do we use these coupling components, then please click on this card above to learn more about it. We'll provide a 12 volt isolated power supply for driver IC to provide the gate pulse. An input pulse will be connected to the in A and in B for both high side and low side MOSFETs simultaneously. We have selected a driver IC, and now the most hectic and time consuming part is to select a gate drive transformer. The important aspect is to calculate or select the required size of the gate drive transformer for our application, and it can be determined by the voltage time product. It must be greater than or equal to the expected value to avoid core saturation. After that, it should have 1:1:1 turns ratio. The isolation voltage rating should be selected for worst case conditions. The leakage inductance should be as minimum as possible, which increases the efficiency and reduces the time delay. Considering all of these inputs, we'll select a gate drive transformer from ICE components. Its primary to secondary isolation voltage is more than 3000 volts. It has a very low leakage inductance of 470 nanohenry. Its operating frequency is between 40 kHz to 350 kHz. All of these parameters of the transformer fulfill our requirement. We have selected the driver IC and transformer. Now we can add a circuit like this at the secondary side to get the optimum switching speed. This circuit helps to increase the turn-off speed of a switching device. We add a turn-off diode along with a gate-on and gate-off resistor with these values. We'll select a Schottky diode as a turn-off diode. If you look closely, the values of RG on and RG off are different. If you want to know why, then please check this video by clicking on this card. The value of the clamping resistor and clamping capacitor is selected as per the application and value of leakage inductance. Well, that's how a transformer coupled gate driving circuitry would look like. I have added all the references related to these circuits in the description. If you have any query, you can ask me in the comment section or email me. Hit the like button and subscribe to my channel. And finally, thank you so much for watching this video.